Hi everyone, my name is Lian Chen and my group mate is Hao Ribo, and I will present our project. Topic is robust motor control design on adaptive speed control of BLDC motors using interval type 2 fuzzer logic. For the problem statements, so it's for BLDC motors facing multiple challenges like nonlinear dynamics, parameter uncertainties, and load disturbances. And for conventional PID controller, it failed to adapt under varying conditions. For the design goal, our design goal is to design a self-turning PID controller using interval type 2 fuzzer logic to improve the robustness. So why we choose interval type 2 fuzzer logic? It's because the traditional type 1 fuzzer logic facing some limitations, like cannot model uncertainties in membership functions and noise input or expert disagreement. For type 2 fuzzer logic, we can use it to do 3D membership functions for handling uncertainty and reduce noise impact and improves the robustness. For the interval type 2 is for simplified computation with interval-based membership grids. And this figure is a basic idea of interval type 2 fuzzer logic controller. For our control design, we have two input, the speed arrow and the derivative of the arrow, and the output is dynamically adjusted KP, K, and KD. And our innovation is modifying the membership function for faster converging and simplifying the rules base for real-time implementation. So this is our simulation in the Simulink in MATLAB. So our test case is for the step response from 0 to 2000 rem per minute, and our simulation time is for 5 times 10 to minus 6 seconds. So it's kind of short time, but we will see the results very clearly for the performance of different controllers. So the first one we use the fuzzer logic controller. And the second one is using PI controller, and the third one is use the PID controller. So for the results of the three of the simulation, we can see the fuzzer logic controller have the best performance, so which was stable in the 0.02 second, and the second performance is for PID controller. It's kind of stable after 0.02, maybe in 0.03 seconds. The PI controller have a worse performance, so it was stable after 0.1 seconds. So our fuzzer logic has the best performance. So the fuzzer rules. So as I mentioned before, the input is speed arrow and the arrow derivative, and output is KP, KI, KD, which is adjustment to proportional gain. And from the figure, we can easily see we got the speed arrow and the arrow derivative. We can get the KP, KI, KD from the fuzzer rules, like which part we will using in the figure. And for the fuzzer rule table for KP, KI, KD, so for the arrow speed arrow, we have a negative big, negative medium, negative small, and 0 positive small, positive medium, positive big, and also for the arrow derivative. So for the result, we have very big, very big, medium, big, medium, small, and 0. So we can see from the table clearly see the input and the result for the input. And the challenging we're facing is turning interval type 2 fuzzer logic membership functions for minimal computation overhead. And the second is balancing the transistor response versus a steady state error. The solution is genetic algorithm for automated rule optimization and to do the trade-off analysis table. For practical application for like where we can use it is industrial robotics like in the high precision speed control. So for the robot, they will have a like a very precise speed control. So we can use the control system, and also for electrical vehicle, it needs smooth torque reduction. So also can use our controller, and also we can address real world uncertainty like temperature drift and again component. So it's not only for the motor, it's also for the other uncertainties. For the future work, our next step is the hardware in the loop testing with Arduino and the Raspberry Pi, and the integration with sensorless control technique. So open question, the ending open question is: can the interval type 2 fuzzer logic handle the multi-motor synchronization? So can it control the multiple motor at the same time? We will figure out for the future. Thank you for listening. We should have a good day.